I'm very happy to introduce Michael Griffin, who will be speaking about distributions on integer partitions.
Okay. Thank you so much, and thank you for the organizers for the opportunity to speak. It's wonderful to be able to speak again after a long time of being able to, having to attend conferences virtually. Today I'm going to be talking about distributions on integer partitions. So this is joint work with Ken Ono, Larry Rowland, and Wei-Lun Tsai. So the idea is this. There we go. Okay. So the idea that we're going to start with, we're going to start off by talking about partitions. And this is the same definition that Olivia talked about, and looking at some of the abstracts, it looks like we're going to have several talks about partitions. So you might see this definition several times, and you'll probably see the same example of a partition several times. So it's fairly standard. A partition is a partition of an integer n is a non-increasing sequence of positive integers which sum to n. And this fairly standard example for talks, P of 4. So this is the number of partitions of 4 is equal to 5, because we can write 4 as 4 or 3 plus 1 or 2 plus 2 or 2 plus 1 plus 1 or 1 plus 1 plus 1 plus 1. And we'll come back to that example in a moment. What we're looking at, what we're interested in is these questions of distributions on partitions. So what we want to have here, we've got a sequence of discrete distributions. So a partition, of course, is going to be a discrete set. And we want to look at these discrete distributions on these partitions. Okay, and we want to look at sort of this limiting behavior of these types of distributions. And our question is, are there examples where this limiting behavior is nice? Okay, so we're starting with these discrete distributions. Perhaps the limiting behavior becomes sort of a continuous distribution. Okay, perhaps we need to normalize things for things to behave nicely. Okay, but are there nice natural examples where as we take these limits and maybe normalize things, these distributions sort of descend into very nice standard continuous distributions? Okay. And of course, the answer is yes, or else I wouldn't be giving this talk. And we're going to talk today about 5 examples. 2 of these are previously known, fairly nice examples. And then I'm going to talk about 3 different problems that I was able to work on. As I talk about this, there's kind of 3 types of tools that I'm going to use. So I just want to talk about this really briefly. The main, maybe one of the main first tools that we're going to use is we're going to use a lot of partition identities, combinatorial identities, maybe some Q-series identities, types of things that a lot of people in this room use a lot. One of the other tools that we're going to use is Hardy-Ramanujan circle methods for asymptotics, sort of analytic tools there. And so this is going to use both of these tools a lot. Okay, kind of combining these 2 tools quite a bit. And then, of course, we're going to come back and use some statistics distribution theory. I'm going to warn you as we talk about distributions, I'm not used to thinking about distributions very much. And so I might say some things that aren't quite right. Hopefully, I'll say things that are mostly right. But hopefully, most of the things that I say are mostly right or right up to maybe some small adjustment. I'm just going to warn you, I just don't think about distributions very much. And so it's very possible I'm going to say some things that aren't quite right there.
See the paper for the
see the paper for the details. We definitely put the effort to get that right in the detail in the paper. If you just ask me right here at the board, I'm probably going to blank. Okay, so let's talk about this first example. This is a very nice example. This comes back to the idea of the rank of a partition. Okay, so the definition of a rank of a partition: you take a partition, you're going to take the largest part, and you're going to subtract off the number of parts. Okay, and so this capital N of m comma n is going to be the number of partitions of little n with rank little m. Okay, so an example of this, the ranks of the partitions of 4. Okay, we talked about those 5 different partitions of 4. Okay, and we're going to split those up. We're going to take the largest part there in that second column there, the number of parts in that third column there. We take the difference, and that's our rank. Okay, so notice that first partition, we get the rank is 3. The second one, we get 1, 0, -1, and then -3 down there at the bottom. Okay, and then we kind of reduce those mod 5. Now this is an interesting thing to do. If we reduce these mod 5, because this sort of relates back to a congruence of Ramanujan. Okay, so Ramanujan said that anytime you take a partition P of 4n plus 5, or sorry, 5n plus 4, that is going to be divisible by 5. He also said that if you take a partition of 7n plus 5, that's going to be divisible by 7. He also said something similar for 11, but the rank doesn't actually explain that one. But it turns out that the rank splits up very nicely for 5 and 7. Okay, so for every A, if you take the number of partitions of 5n plus 4 that are congruent to A mod 5, you're going to get exactly an even distribution there for those partitions. Okay? And you'll get a similar thing for 7. Okay? They split out perfectly evenly, and so that explains Ramanujan's partitions for 5 and 7, okay? Because these are perfectly even. Now, generally, this is not the case. They're not going to be perfectly distributed that way. However, Brinkman in 2008 showed that on average, they are evenly distributed. Okay? And so if we take n of a comma b for n, and then we divide by p of n, we let n go to infinity, we get exactly 1 over b. Okay, so for each congruence class mod b, the number of partitions of n, or the proportion of partitions of n, with rank congruent to a mod b is exactly distributed, okay, correctly, so that you've got just 1 over b. So we get this nice even distribution. Okay. Another example that we'd like to talk about is the number of parts. Okay. Yeah.
So we have this nice generating function for rank.
Yes.
I've not seen Brinkman's derivation, but is it the case that basically what you do is you put the roots of unity and then calculate and then asymptotically show that each of those sums to the roots of unity and their powers is little o of the apps of the sum, so that it has to be a uniform distribution?
I'm not exactly sure on that. I haven't gone through Brinkman's paper. I believe that there's a part that's going to be very similar to that. I think you're probably also going to need the asymptotics for both the standard partitions and the asymptotics for the rank, both of which are known and which can be derived from the circle method. But I think you're going to need to combine both of those ideas there. Yeah. Okay. Yeah. So let's talk about another example here. This is the number of parts. Okay. So the idea here is we're going to take our partition function, and so usually the coefficient, you've got a nice generating function for the partitions. The generating function for all of your partitions is going to be this product over 1 minus q to the n. So if capital T were just 1 there, that would give you the generating function for the partition numbers themselves. Introducing this t here is going to split things up. And so now what you're going to get, these coefficients of q to the n are going to be polynomials in t, where the particular coefficients here are going to tell you how many partitions have that many parts here. Okay, so you can see in this table here. So for instance, in that first row, we've got partitions of 4. That first line there tells us that there is 1 partition into 1 part. Okay, so that's the partition just 4. Okay, we've got 2 partitions into 2 parts. So that's 3 plus 1 or 2 plus 2. Okay, we've got 1 partition into the 3 parts, and we've got 1 partition into 4 parts. Okay, and so that's what you end up getting there. And if you work with these types of generating functions, it'll probably take maybe a minute to recognize how that works out. But it's a fairly standard argument that this generating function can give you this number of parts polynomial. Okay. Now, one thing to pay attention to here, this is not symmetric. Okay, you can expect that the degree of the polynomial is going to be the same as n. That's because you're always going to have the partition 1 plus 1 plus 1, etc. n times. Okay, so we know the degree of the polynomial. It's going to be fairly large, but kind of the size of these coefficients is kind of weird, and it's not a symmetric polynomial by any means, but it does kind of bump and then drop back down again. So Erdős and Lehner studied this polynomial, and they showed that these number of parts satisfy a nice distribution property. Okay, so the notation that we're going to use here, we're going to use this piece. We've got a less than or equal to k there and a subscript of n. So this is going to be the number of partitions of n with less than or equal to k parts. Okay, so so less than or equal to k parts. So if k is 3, we're going to look at the partitions into 1 part and the partitions into 2 parts and the partitions into 3 parts. Okay. And what they showed was that we get this very nice distribution function, cumulative distribution function for the proportion of partitions that satisfy this property. Okay. So we're looking at the proportion of, so for a fixed parameter k here, we're looking at the proportion of partitions that so that the number the proportion of partitions with less than or equal to k parts is given by this distribution. Okay, so now the way that they formulate this equation, we're going to take kn is equal to this expression here. So notice we've kind of got this. We've got this description here that depends on x. We've got a part here that stays kind of constant here. And then we've got sort of a deviation here that depends on x. So kn of x is equal to this plus square root of n times x. Okay. So that kind of centers our distribution here a little bit and kind of rescales things. And what we end up getting here is this particular kind of strange looking distribution. This is what's called a Gumbel distribution. Okay. So they showed that we end up getting a Gumbel distribution here. Okay. By the way, this first part here in this kn of x, this c inverse times square root of n log n, that is the normal order for the number of parts. Okay. So this is something that I'm probably going to get wrong. This isn't exactly the mean for the distribution, but this is sort of the greatest probability for number of parts is going to be close to this number. This is sort of the peak on the distribution function. Okay. And so what you're looking at here is you've kind of got, this is the point for the peak plus this kind of variation here times x, and the deviation times x. Okay. And so we end up getting this Gumbel distribution. The cumulative distribution function is going to look like this. So as x gets very large, we're going to get closer and closer to 1. Okay. So that's going to be our integral over the distribution. And so, of course, as that goes to infinity, you're going to hit 1. And so now let's, so this was Erdős and Lehner's theorem. Let's compare this numerically with the actual data. Okay, so in this table that I'm going to show you in just a moment, we're again going to use this notation. Kn of x is going to equal this function here. Delta is going to be the true distribution for a fixed n. Okay, so actually the number of partitions, the actual ratio or proportion of partitions of n with less than or equal to kn parts divided by p of n. And then the Gumbel is going to be, that's what we're seeing as our sort of limiting distribution. Okay, so the Gumbel should approximate the truth. The truth is given by delta. Okay, and so this is what we see here. So we're looking at n here is 750. We had to go kind of a ways out to see this converge. Okay. Notice that there are a very large number of partitions for 750. Okay. But what you end up getting here is generally the sort of expected number of partitions satisfying, what am I saying here? So K here, so sort of the expected number of parts is going to be somewhere around 80-ish, okay? And so when K is close to that, we start getting a little bit larger than that. You can see that delta gets close to about around 2/3 and then starts moving its way up to 1. You can compare that to the Gumbel distribution. And initially we're just a little bit shy, but we get fairly close fairly quickly. Okay. So this is a fairly good approximation. You can see kind of the error is there and maybe in the 100th place there, but it's a fairly decent approximation. Okay. This is sort of this statistic property, this sort of distribution property we're seeing with the number of parts of a partition. So the first project that I worked on in this line, this is with Ken and Larry and Wei Lun. We wanted to generalize that idea of the number of parts. Okay? And so now what we're looking at is, instead of just the number of parts less than or equal to k, we want to say, let's look at the number of parts that are divisible by some number a. Okay. So we're going to define this p less than or equal to k of a comma n. So this is the number of partitions of n with no more than k parts that are divisible by a. Okay. So for example, when a is 1, this reduces to the previous example. Okay. But we're looking at larger than that. So for instance, when a is even, we're looking at no more than k parts that are even, or so on. Okay. And we want to look at this proportion of partitions that satisfy this property. Okay. So what is this cumulative distribution function? Okay. So it turns out that we're going to create some similar numbers here. So C is the same thing that showed up in the previous example, that is an important number kind of in the asymptotics for the partition numbers themselves, this pi times root 2/3. Okay. So our Kn here is going to be very similar to what we saw before in the Erdős Lehner case. The dependence on A shows up right here in the denominator, but it doesn't show up there in that secondary term. Okay. So just there in that denominator. So 1 over AC root n log n plus root n times x. Okay. Then what we find is that the limit of this proportion is equal to, again, this exponential. So again, this looks very similar to this. This is a Gumbel distribution in this case, very similar to the previous example. But now, again, we have this dependence on A that shows up both here in the, well, I guess we've got a double exponent here. So both in this denominator of the exponent and then in the exponent of the exponent. Okay. So both of those places here. Okay. So similar to this previous case, it is a Gumbel distribution. Okay, the mean is given in as shown here. You can see the dependence on A. The variance is 1 over A squared. And this reduces exactly to the previous case when you take A equals 1. And so to me, it was kind of surprising seeing this, that the dependence on A shows up so simply. It wasn't obvious to me looking at the problem that generalizing the question in this direction would make such a nice alteration to the formulas. But as you can see, it seems to be a fairly natural alteration there. Let's see. So let's look at some numerics in the A equals 2 case. So again, we already looked at numerics in the A equals 1 case, the Erdős Lehner case. So in A equals 2, we're looking at, we want the number of partitions of n with less than or equal to k even parts. Okay? And we've got our Gumbel distribution. So delta is going to be the truth, okay, actual numerical calculations for a fixed n. And then Gumbel is going to be our limiting distribution, what we expect to approximate the truth. And so this is what we see. Again, we're looking at n equals 600. We didn't have to go, you don't have to go quite as far to see this look nice for A equals 2, but we still need to go out quite a ways. And here you can kind of see this, what's coming out here with the Gumbel distribution. Okay. And as you can see, kind of we start off a little bit small, but it catches up fairly quickly. So the truth is at 600 is sort of underneath the asymptotic curve initially, but we catch up fairly quickly. Okay. Let's see. So this theorem is based on some asymptotics that we had to come up with for this particular paper. As far as I know, these are not in the literature prior, but we did come up with these asymptotics. They're kind of ugly looking, but if you stare at them, get to know them, they're not too bad. In particular, you notice that if you plug in a constant for A, things tend to collapse pretty quickly. The dependence on n is just in a few very specific places. Okay? So for specific values of A, it collapses really nicely. Okay? So we ended up coming up with these asymptotics for both P less than or equal to K, as well as, so PK here is, this is when we want exact. Okay? This is when we want to know exactly, sorry, partition. So let's see, before we're looking at less than or equal to K even parts, or parts divisible by 8. Here we're looking for exactly K parts that are divisible by 8. Okay. And we have these asymptotics for both of these. We do need stronger asymptotics than these specifically for the proof itself, because we have error terms. In fact, we have error terms up here in the exponential that you have to account for. And so it's not enough just to have these asymptotics, but we're able to combine these with some other identities involving kind of some combinatoric identities to be able to get what we need out of this. We'll come back to that. We'll come back to that proof in a few minutes here. Okay. Another quick example here. When A equals 3, K equals 1. Okay, so what we're looking at here is exactly, well, so P of 1 here. So we're looking at exactly one part that's divisible by 3. Okay, we have a nice asymptotic formula for that. Okay. And as you can see here, it seems to be a decent approximation of the truth. Okay. And so this is to me kind of an interesting property. Again, I don't spend a lot of time thinking about partitions and all of these different partition statistics directly, but it's a little bit surprising to me that we can get these precise asymptotics for something so specific as the number of partitions with exactly one part that's divisible by 3. So to me, at least, that's a fairly interesting
I do have a question.
result here. Yeah.
Yeah, it seems like this is kind of just like the first term of like a Rademacher type formula.
Yeah, exactly. So that's, so Rademacher formula is that first term is going to be just kind of that main term from the Hardy-Wright circle method.
So, I mean, can you push it so that you get
sure
first finite number of terms?
Yeah, so first finite number of terms to get an exact convergence sequence might be a little bit more difficult
Yeah,
here.
of course, that's
but yeah, you certainly could get those, those first several terms for sure. Yeah, absolutely.
Michael?
Yes.
In fact, if you only are putting that previous one.
Oh, this one?
Yeah.
Oh.
If you're only putting a asymptotic, then you don't need an n minus 3 to the 1/4. It's just n to the 1/4. But you put that n minus 3 to the 1/4 if you can get a second term, and that's my here of genuinely smaller order of magnitude.
Yeah. So that just gives us a little bit more precision. Again, for our theorem, we needed something even a little bit more precise than this, but yeah.
So do you see a cluster sum at all? Yeah.
Not the way that we did this. We weren't trying to be precise enough to see Klusterman sums shown. Yeah.
Because I think this paper of Riemann from 2008, if it's the paper that I'm thinking of, the model transactions, there's some kind of Klusterman sum like thing in that.
Yeah, for sure. And usually that's the sort of asymptotics I'm a little bit more. I work with more commonly. I work with the Poincare series, and we get these nice, in general. I don't often work with these types of approximations, but this was a little bit more the better tool for this particular application for sure. Yeah. Okay. So let's move on to a second problem. So the second problem we wanted to look at are T-hooks. Okay. So given a partition, we can create a Young diagram. So for instance, if we've got the partition 5, 4, 1, this is a partition of 10. Okay. You kind of arrange boxes. So we've got 5 boxes up top, 4 boxes 1, corresponding to the parts of our partition, right? Okay. And then in each of these boxes for the hooks, what you write is the number of boxes below and to the right of the box, including itself. Okay. So up here, we've got a 7 because we've got 5 plus 2. Okay. 5 to the right, 2 below, and then 1, or sorry, 4 to the right, 2 below, and then 1, including itself. So that hook for that particular part is 7. Okay. And then you can fill in the rest of these boxes similarly. Okay. And so now we have this question. Suppose you want to look at the number of partitions or the number of some value t that show up in these partitions, okay? Or so the number of some value t that show up in these. Does that distribution have a similar limiting behavior? So let's look at an example here. So we look at these partitions of 5,000. So these are all of our partitions of 5,000. Okay, we're going to break up our, we're going to create this polynomial here in T, where the exponent is the number of 2's that are showing up in each of these, showing up as a hook in each of these partitions. Okay. So we end up getting this, and now we start plotting these coefficients, okay, and you get this really nice kind of bump function. Okay. And so, of course, 5,000, the number of partitions of 5,000 is huge, astronomical. Okay. And so even though that second term there looks enormous, you'll notice that that corresponds to basically nothing there on the graph, right? We have to come all the way out here past like 50 before we start seeing this blip up here. And that's on the order 2 times 10 to the 73. Okay. And so these are huge astronomical numbers, but we do get this kind of nice, smooth looking curve here. So we were actually able to show that asymptotically, the distribution that we saw on that previous page, that is a normal distribution. We have the mean of it, we have the variance of it, and that depends on t. The mean depends on t in kind of this really simple way. The mean, primarily you've got a square root of 6n over pi, but then we just shift that over based on t. And then the variance here, at least the main order term here, doesn't depend on t at all, which I think was a little bit surprising. Okay, so really our dependence here for this distribution really is just a little bit of a shift there on the mean. Okay. If we let k be, we're going to take the mean and then add x times the standard deviation, square root of the variance. Okay, so that's going to kind of center us right there on the peak of the distribution, and then we'll look at how far to either side of that we go. Here we get the standard normal distribution function, standard normal cumulative distribution function. And so this is something that I think was a little bit surprising. When we started this project, we were kind of expecting to see something similar maybe to a Gumbel distribution or something here again. It's a little bit surprising to see that in this particular case, we get something that's normal. And nothing against Gumbel distributions, but personally, I think normal distributions are very beautiful. So it was really, really nice, a very pleasant surprise to see a normal distribution show up here for these T-hooks. So let's do an example again. So we're gonna take T equals 2. So this is the number of 2's that show up in the hooks of these partitions. Okay. So we're gonna let D be our true cumulative probability distribution. E of x is going to be that's going to be this right-hand side. So the pure normal distribution. And we take the ratio, okay, and you can see initially, so if we come a little bit to the left of the bump, we're a little bit undercounting, at least compared to the normal distribution. Right at 0, so right at the mean. In this particular case for 5,000, we bump just a little bit above the true normal distribution, and then we come back down a little bit, but it's all very, very close here, okay, within about 1%. Okay. So our problem 3 is a variation on problem 2. Okay, so problem 2 was looking at the number of this value t, whatever that is, that actually shows up in the hooks for the partitions. The second one is, instead of how many t's actually show up, we're looking at how many multiples of t show up. Okay. So this will be slightly larger, but it turns out that the analysis for this is not that much different. And so these problems kind of naturally came together. Okay. So this y hat here, this is going to be the distributions of the number of even hooks in the partitions of n. Okay, y hat t is going to be the distributions, the number of hooks that are divisible by t. So this is what we want to look at here in this problem. Okay, so for example, we'll let t equal 11, take n all the way up to 1,000. Again, these numbers are astronomical, not on the same scale as previously. We're only going up to 10 to the 30th instead of 10 to the 70th, but still get kind of a smooth bump here. This one's not normal. No, this one does not look normal like the previous one. Okay, but it is still kind of a nice, pretty little bump there. And you can look at this and kind of suspect that there is kind of a nice distribution going on here in the background. Okay. So it turns out that this is a shifted gamma distribution, which, yeah, I don't actually understand the shifted gamma distribution very well, but this is what we get out of it. Basically, so a definition, so a random variable is gamma distributed. You've got these two, so you've got a parameter and scale, parameter k and scale theta, and you end up getting this particular distribution function. So you've got an exponential part, a polynomial part, and then we're kind of scaling everything by this gamma factor, the gamma term. Okay. So this is what it means for a random variable to have a gamma distribution. Okay. Now ours is actually shifted, and so what we end up getting here is over here on the right, you see sort of a true gamma distribution, particular scale and parameter, but then we've got to modify this a little bit here. Now notice for this theorem, we have to have t greater than or equal to 4. Okay. But with t greater than or equal to 4, we end up getting this particular distribution. We have, we can calculate the mean and the variance, okay? Just modifying those calculations for the gamma distribution itself. Okay. And once again, if you take k and you set it equal to the mean plus x times the variance, so again, pick the mean and then we're looking at our shift either side of the variance, then our cumulative distribution becomes sort of this normalized lower incomplete gamma function. Okay, so that's the distribution that we see on these t hooks. Okay. Now we have to have t greater than or equal to 4. We tried to, it would be nice to have, so in the previous example, you could take, so I guess not the previous one before that, you could take a equals 1 and you exactly get Erdős Lehner. That's really nice here. Here it would be really nice to be able to consider things, you know, with small t here. And this doesn't scale nicely for 2 and 3. It just breaks down. Okay. The problem there is we know that there are always vanishing terms there in the polynomial, so it's not going to be a continuous distribution. Okay. There might be some way to modify some things to kind of extract a meaningful distribution here in the middle, but at least using, at least approaching it the way we were, looking at it the way we were, there's not a meaningful, there's not going to be a meaningful limit for 2 and 3. So let's see. So again, just some examples to kind of illustrate our approximation here. So our cumulative distribution function here. So on the left-hand side, that's going to be our truth, okay, actually counting the hooks. On the right, we're going to have our continuous approximation. And again, you can see that at n equals 1,000, we get a fairly good approximation. Okay, not quite as good as in the previous example, but fairly close. Okay, so for x minus 1, we're about 90% there. By the time you get positive x about 5/4, we're very close. Been about 1,000. Okay, so those are the examples that we had of these partition statistics that have these very nice distributions, these continuous limiting distributions that we studied. Let's go ahead and take a few minutes to look at some proofs here. Again, as I talked about, these proofs are going to combine these tools of some combinatorial identities, just using the partitions themselves, as well as asymptotic behavior. Okay. The first proposition that we need, this is a purely combinatorial identity. This is going to give us a way of summing up the number of partitions. Let's see. So this is the number of let's remind ourselves of this notation. This is the number of partitions of n with no more than k parts that are divisible by a. Okay. So all of those terms. That's what we're looking at here. Okay. Now it turns out that we can write this as sort of a convolution sum, okay, in this way. And the reason why we would like to do this allows us to write it. One of these terms is just going to be p less than or equal to k of j. So this piece right here, that's the piece that Erdős Lehner studied. We already understand that a little bit fairly well from their work. And then on the right-hand side, we've got the p regular partitions. Okay, so these are the partitions of whatever this argument. So the partitions of that second argument, which do not have any parts divisible by a. Okay. No parts divisible by a. Okay. So the way that this identity works, okay, you can take a partition. So any partition that we're counting over here on the left-hand side. So this is going to be a partition of n, which has no more than k parts that are all divisible by a. We're going to split that partition up into the parts that are not divisible by a at all. Okay, those are going to correspond to a piece here in a p regular partition, and then the parts that are all divisible by a, which we can then factor out in a. Okay, so we're going to take this partition, split it up, something that's a regular, and then adding on to that a times a smaller partition. Okay, now this smaller partition here needs to be counted by this piece. Okay, we want to have no more than k parts that are divisible by a. So then when we factor out a from that, that's going to be a partition of this number j with no more than k parts at all. Okay. And so we're just taking sort of this direct sum that gives us this kind of convolution sum, allowing us to relate this thing in terms of these slightly simpler expressions. Okay, now Erdős and Lehner in their work, they showed that this p less than or equal to k of j, because we want to take j, we want to count the partitions into no more than k parts. Okay, they're able to write it in this way, again, writing it in terms of something simpler, so the standard partition function, and then we're going to subtract off this piece over here. Okay, this is kind of weird looking, but kind of the idea here is what we're looking at here. So M is how do I want to explain this? The idea here is that this is sort of counting partitions with we could say more than k parts, or maybe an easier way to think about this is just by conjugacy. If you take a partition, take its Young diagram and kind of rotate the Young diagram, you get what's called a conjugate partition. So if you're looking at partitions of no more than k parts, the conjugate partition is going to be a partition into parts, none of which is greater than k. So what we're sort of doing here is we're taking our partitions of j, and then we're going to subtract off, when n is 1, you're going to subtract off all of the parts, or all of the partitions of j minus something larger than k. Okay, so we're gonna subtract every partition that contains a k plus 1. We're going to subtract off all of the partitions that contain a k plus 2. We're going to subtract off all the partitions that contain a k plus 3, and so on. Okay, so that's the m equals 1 case. Now we've overcounted, right? We've subtracted off too many pieces, because there are some partitions that contain both, say, a k plus 1 and a k plus 2. So we need to add those back in. Okay, so that becomes sort of an inclusion-exclusion argument here for this kind of count. Okay. And so that's how they were able to take our partitions of we want to end up with partitions into no more than k parts. We're going to start with our total number of partitions and do this inclusion exclusion to kind of subtract off everything that we don't want. So that's sort of what we did here. Okay. Now, okay, we have this identity up here, this first identity. We talked about that one. Okay, Erdős Lehner gives us this identity. We can just kind of plug that in right here. And at this point, everything is equality. These are all combinatorial identities at this point. Okay. Then we're going to normalize everything. We're going to divide by P of n, because again, we're interested in these ratios. Okay, that's where things are going to look nice as we approach limits. Okay. Next step, this piece here in the middle, it turns out behaves fairly nicely if we divide by P of j. So we're going to try to normalize this piece in the middle by P of j. Of course, that means we've got to multiply by a P of j up here on the right. Okay. But this inner sum here, we've taken those SKs and we've divided by P of j. Turns out those have fairly nice asymptotic properties. Okay. Erdős Lehner showed that they look like this. Okay. So you've got this piece here in the middle, which is, it's not too terrible, but we can kind of ignore that for the moment. The main thing to pay attention to here is you've got a 1 over n factorial times something raised to the nth power. And we're taking a sum over all m's. So this piece right here is going to, and then we can, So we've got this sum, 1 over n factorial, is this thing all raised to the m. This is going to look like an exponential. Okay, right back down here to a 1. Okay. Now this asymptotic here, we do have to be careful about error terms and so on, but Erdős Lehner they handled all of that very carefully, and we do get that this is actually asymptotic to this single exponential term. Okay, and that's going to turn into that's why we end up having sort of this exponential inside of the exponential in the Gumbel distribution. Okay, so now our term looks like this. We've got our sum. That inner sum right there just turned into this exponential. Now we've got this right-hand part that we've got to deal with. Okay, the P regular partitions. Okay, we have Hardy-Ramanujan congruences for P of j, and then Haggis has not congruences, asymptotics for P of n, and then Haggis gives us asymptotics for P regular. So this is an important aspect here that we're able to use. We're able to plug that in here, and combining these asymptotics together, we're able to get this kind of this expression. It's kind of obnoxious, but again, it's not too bad. There's just lots of pieces. None of the pieces are terrible. Okay, we're gonna set j equal to this particular term. It tends to collect things a little bit nicely. Okay, so j was kind of our index in the summation, allows us to collect things a little bit nicely here. And then as we take a limit, we're able to reduce things into these pieces. Let me skip ahead just a little bit. Right down here at the bottom, we're able to collapse things into this piece where the only dependence of n is just in these limits of the integral. Okay, it makes it very nice. As n goes to infinity, we're just taking this integral, going all the way from minus infinity to positive infinity. Okay, and that gives us our Gumbel distribution. And so that gives us exactly this. Our limit is this exponential of this piece times the exponential of this side. So that is exactly our Gumbel distribution. Okay. So definitely some kind of technical work there in the middle, but not too terrible. Mostly just using these combinations of these asymptotics and these Q-series identities, not Q-series, these combinatorial identities. The problems, yeah, go ahead.
So it's been sort of blowing my mind a little bit, the formula for case of n, just thinking of your theorem.
Mm-hmm.
You know, just the feeling that the number of parts you're allowed to have will increase with n from that formula.
Yeah.
And I guess I thought I would understand after you talked about the proof, but I don't think I do. Is there like an easy way of seeing where that formula for case of n comes from? Or is it just like this is what makes the proof work kind of thing?
So it's sort of the thing that works. It's kind of weird. Like you go through it, and basically you have to have that particular K-sub-n in order to get the dependence on n to kind of factor out. Right. And so that's really what it is. You just find that that's the right answer. And I don't have a better answer than that, but it's just the one that works in there.
Before, right? You could go back to the envelope, like not rigorous proof heuristic, and you can see that that's just, as you say.
Yeah. Yeah, and I don't know. It's the one that works. It's the one that makes things cancel out. And
yeah. But if you're just like sitting in the audience, there isn't necessarily something.
No, I don't have a good way. I don't have a good way of saying that.
I think it's what just comes out of the saddle point method when you look at the K that works.
Yeah. You change it to the right or left at all, and your saddle point just doesn't work. It just go up. Okay. Let's see. So yeah, we're just about out of time, but let me just really quickly say something about problems 2 and 3. So again, the analysis on those are fairly similar. We end up having fairly similar generating functions that we're going to look at here. These come from Hahn, and this is a really important tool here. We couldn't do any of this work without these two generating functions from Hahn. Okay, so these are going to count our. So this first one is number of times t itself shows up in the hook lengths, and the second one is the number of times the multiples of t show up in the hook lengths. Okay, and Hahn gives these beautiful exact generating functions that give those. Okay. It turns out that we're able to give formulas for these. Again, these are sorts of things that you could get exact formulas using Rademacher type sums, but just using the circle method, we're able to get these first order terms. These ones are kind of interesting because we end up getting this dilogarithm that shows up here, which is kind of weird. But we end up having that one there. Let me skip ahead just a little bit. We end up using certain identities for logarithms and dilogarithms, the sums of logarithms and dilogarithms. Able to connect those using Hahn's functions and these similar technical saddle point calculations. And a lot of the analysis isn't too different from the previous examples. Just the saddle point method, things kind of break apart a little bit differently. And at the end of this, we end up getting moment generating functions, especially for the third project. It was kind of hard to see like exactly the probability function that was coming out of it. It was easier for us to calculate the moment generating function and then compare that the moments for the gamma distributions. That was much easier than, especially where it's a shifted gamma distribution, and none of us being actually experts on gamma distributions. That was the easiest way for us to work through that. Okay, so just a quick review. We have these theorems. Our first theorem here is this distribution for the number of, so proportion of partitions of n, so that no more than n parts are divisible by a, gives us this nice Gumbel distribution with the mean and variance coming out exactly from that distribution. And then we have for these parts where we're counting the t's that show up in the hook lengths, that comes out to be this very nice normal distribution. And then in this case where we're looking at the hook lengths that are divisible by t, we end up getting this shifted gamma distribution. It comes out just like this. And again, with explicit means and variances that show up. Okay, let's call that good. Thank you for listening to my talk.
Thank you, Michael, for a really interesting talk. We have time for maybe 1 or 2 questions. Yeah, here, let's get the. Maybe I didn't. Let's put this one over this side.
That's not working either.
Well, maybe you can speak loudly.
Sure. Okay. Yeah. About the rank, Brinkman's result, the equidistribution. Do you know, or does anyone in the audience know if there's a combinatorial proof of that, especially like for b equals 2? So even odd rank, can you prove that the proportion of partitions with even odd rank is a half?
Yes.
You know, does anyone know that?
I don't know.
The difference of common view.
I don't think that's a common rule.
Yeah. So the
Yeah, because that's a remarkably simple.
right. It's a remarkably simple statement. The issue that I would have there is the fact that you're taking a limit. I feel like you've got to involve some asymptotics somewhere.
But this error term for the difference is very delicate analytically. These are coefficients of FQ. There's a given by a series of Christian sums that the full force of respect to the bottom of So I don't know about anything kind of combinatorial.
Yeah, so there isn't some like involution, I suppose, that almost involution between the even and odd rank, because it gives you this FQ, which itself is very delicate. So maybe we think there isn't a combinatorial.
Yeah, I certainly don't know of one. I don't think that Brinkman's. I definitely don't think that Brinkman's work implies an easy combinatorial proof.
Maybe one more quick question.
Just curious about the rated convergence to the distributions, because I noticed like with numerics, sometimes they were really close, and sometimes they were a little bit.
Yeah. Yeah. So if we worked harder and got a better error term, or a little bit more precise on the error term, then that should tell us that rate of distribution. But yeah, we didn't push hard enough to get a really good description for that.
I was thinking, especially with your the PK P up to K ANs, you have everything in terms of the regular partition numbers and then the partition numbers. And you have Rademacher formulas for all of those, and I think maybe even like effective error asymptotic bounds. Yeah,
I'm sure that's doable, and I'm sure that I'm sure that's exactly all you would need to do. You just need to keep track of all of those extra error terms. I think they're all there. You just need to do the work, and we didn't care enough, I think, to get all those precise error terms. But yeah, that's certainly, I'm sure that could be done.
Let's thank Michael again for his talk.